Welcome, everyone, to Space Geek Speak on this fine Saturday, December 14th, 2024. Welcome, everyone. We have a great speaker today, Jim Cavera, and we appreciate him getting up early, his time, and we appreciate everyone else in all the other time zones around the world who are joining us today. So Jim's got an exciting talk, and just a few words of background on Jim. He's currently in independent consulting. He did his graduate work in nuclear engineering and aerospace engineering, and during that time, he explored the use of dense plasma focus devices for interstellar travel. So that sounds exciting. And he has served for many years on AIAA's Nuclear and Future Flight Technical Committee, and he's currently the chair of that committee. So he's doing a lot of research, and we really appreciate him taking his time. He's got a set of slides. He said he'll make those available after the presentation. So go ahead and take it away, Jim.
All right. Thank you very much. Just give me a quick thumbs up if you can hear me okay.
Yes.
Good. Excellent. All right. The purpose of my talk is not to exhaustively talk about everything that's going on in the world of nuclear space propulsion, because that would be like 3 or 4 talks easily. What my goal here is to tell you a bit about what's taken place in the past, what is currently being researched, and also how we can extend that a little bit into the future, what we could possibly do. As another goal, I would like to give you a little bit on nuclear physics so that you have enough information to evaluate these new concepts on your own as they come up. We're going to start off with nuclear physics and then go into a little bit about what's come before, terrestrial reactors, NERVA, rover, that kind of thing. And then we're going to start talking about ideas for nuclear propulsion in rough order of scariness, from least scary to, oh my gosh, what were they even thinking? Scarier, liquid core, gas core, fission fragments, and then ending up with the holy crap, how could anyone even consider doing this kind of ideas? All right, so let's get started on nuclear physics. But first, here's why we need all of this in the first place. Because the rocket equation is terrible. Here's what we have today. These are some rocket engines that were or are in use now, and their rough specific impulse, a measure of efficiency, as well as their thrust. So as you can see, our normal sorts of chemical rockets have a specific impulse that ranges from around 250 seconds up to about 450, with thrust in the hundreds to thousands of kilonewtons. And this is pretty normal. There's some trade-off between efficiency and thrust, of course, because there always is. But this is what you commonly see. The most efficient rocket engines that we have right now that are either in use or in work, they max out at about 460 seconds. And with a liquid hydrogen, liquid oxygen engine, from an engineering standpoint, that's about as good as we're going to get. In theory, liquid oxygen, liquid hydrogen can get up to about 510 seconds. But engineering-wise, we can't quite get there. You'll notice at the very bottom, we have the N-Star engine, which was used on the Dawn mission. And you can see this has very high specific impulse. It's very, very efficient, but a really low thrust. And that is here as a contrast because this is an ion engine, not a chemical engine. It doesn't use thermodynamics. Instead, it accelerates the propellant via means of electrostatic force. So the engine can have a much higher efficiency, but at the expense of thrust. Ideally, what we would like is something with that good of an efficiency, but also a very high thrust. And here's why. This is, in fact, the rocket equation. And if you plug in the numbers, so let's say you want to go 5% the speed of light. You put in the numbers, you end up needing more stuff as propellant than probably exists in the known universe. Now notice that ISP, that specific impulse term for our efficiency measure, is right up there in the exponent. This means that we can get a really good performance increase by even moderate efficiency gains. So that's what we want to do. And here's a hint as to how we can get there. This is a handy chart of fuel energy density in megajoules per kilogram. You'll see the things that we normally burn are, right in the tens-ish of megajoules per kilogram. Liquid oxygen, liquid hydrogen, they have a fuel energy density of 80 megajoules per kilogram. So right in line with that other stuff. Uranium, on the other hand, is many orders of magnitude above that. So hey, here's an idea. Let's use some uranium. Maybe we can get a lot of efficiency out of that. Here's how we can do that. Step one, we get some neutrons. Step two, we get some stuff that splits apart when a neutron hits it. Spoiler alert, that's going to be uranium. Step three, we make sure that there are enough extra neutrons to keep it all going. And then we just stand back and let it do its thing. All right, so let's start getting into the nitty-gritty of this. There is a figure in the nuclear engineering world called N, or reactivity. Sometimes it's called K, effective, depending on the literature that you read. And this is simply the ratio of the number of neutrons produced by the reaction over the number of neutrons needed to sustain it. So this number depends on the fuel that you're using, all of the materials in the reactor, the ones that absorb neutrons, the ones that reflect neutrons, the one that moves neutrons from place to place, reactor temperature, geometry, and because, of course, quantum mechanics is weird, there's a random element to it as well. Here are typical values. If N is less than 1, the reactor is called subcritical. You're not producing any excess energy, and it's just sitting there slowly cooling down. At N exactly equal to 1, the reactor is called critical. And unlike every science fiction show ever, when a reactor goes critical, it doesn't mean it's about to explode. All it means is that you're at the break-even point where you can start to produce a little bit excess energy. For a commercial reactor, the kind that we use on Earth to produce power, they generally want to keep N somewhere between 1 and 1.1-ish. That is sort of the happily sitting there generating excess electricity point. If N gets above 1.1, then reactor operators start to worry. If it gets above 2, they start to run. If N is above 50, then you've basically just detonated a weapon. So sometimes reactivity is measured in dollars and cents, and I'm not sure why they picked dollars and cents. I guess they just needed a name for the unit back in the 40s, and that was what they chose. Anyway, less than a buck, the reactor is subcritical. At $1, the reactor is delayed critical. $2, it's prompt critical, and I'll explain what those mean in a bit. And at about $1,000, again, you've just detonated a bomb. Where you see these different numbers depends on the type of literature you're reading. Dollars and cents is usually used in nuclear engineering literature, whereas reactivity, measured as a ratio, is generally used for regulatory and reactor operator kinds of literature. Okay, so this is our standard reaction cycle. We start with uranium-235. We chuck in a neutron. It briefly, and by briefly I mean for about a femtosecond, it becomes uranium-236 in an excited state, and then immediately breaks apart into two other things and a few extra neutrons. So, kind of like in undergraduate chemistry, you learned that whenever you burn a hydrocarbon and oxygen, you always end up with CO2 and water vapor. Which, yeah, that's mostly true, but a lot of other stuff goes on the side. And if chemistry were that simple, then we wouldn't need emission controls on cars. But it's not. And nuclear reactions are the same way. A lot of different reactions go on at the same time. In our standard reaction cycle example, We have the uranium-235 breaking into krypton and barium and 3 neutrons. But it could also equally well release a gamma ray or break up into strontium and xenon and 2 neutrons, or rubidium and cesium and 3 neutrons, and so on and so forth. But then bear in mind that those things that it breaks into are also unstable, and so they decay. For instance, krypton 92 could break up into a extra neutron and rubidium 91 and a beta particle. Or it could end up as 2 extra neutrons and a beta particle and strontium 91, and so on and so forth. Again, there is a lot going on simultaneously. Which brings us back to the whole prompt versus delayed reactivity thing. So the neutrons that come right off the uranium nucleus are called the prompt neutrons because they're available instantly to go and create other splitting kind of reactions. The ones that come off of the decay products, those are called delayed neutrons because they come off more slowly in terms of time scale. So Krypton 92 has a half-life of a couple of hours. So those neutrons aren't coming off instantly like the ones from the uranium. But because, the uranium doesn't care where a neutron comes from when it wants to encounter a neutron and split apart, you got to account for all of these in the reactivity calculations, which gets very complicated very quickly. So if we go back a couple of slides here, at a buck, a reactor is delayed critical, meaning it is critical if you account for all of the delayed neutrons. At $2, a reactor is prompt critical, meaning it's critical if you ignore the delayed neutrons and only account for the prompt neutrons. So a reactor operator likes to keep the reactivity a little over $1 because, all of those other neutrons still exist and they're still coming out, and you still got to make sure your nuclear reactor is happy, but not too happy. Okay. So, like I said, reactions are a mess. But fortunately for us, quantum mechanics runs on statistics. This is a rough graph of the decay products that you get. And note that the decay products that you get tend to split in size, one being roughly twice the mass of the other. And that is a general statistical trend that nuclear reactions follow for various quantum mechanical reasons. Note also that there are 2 graphs, or 2 separate plots on this graph, one for fast neutrons and one for thermal neutrons. And, that's a little hint as to what's coming next. I will explain the difference between the different types of neutrons in a bit. Okay, again, chemistry is easy. We have 92 naturally occurring elements and a bunch more nowadays that another 30 that we're up to that have been artificially created. And that's it. Reactions liberate a few electron volts of energy. They take place on time scales that are easily measured to us with human clocks. And everything is pretty straightforward. Nuclear physics throws a wrench into the works. We no longer care how many electrons are in the electron shell or what shell they're in. We only care about the protons and neutrons. Here is the chart of the nucleotides. It's kind of like the periodic table of elements, except for all of the things that are interesting to nuclear physicists. So all of the stuff in black is the things that we commonly see and the things that are most stable. As you go off this kind of middle axis, things get more and more wild. Also, as you go up and to the right, things get crazier. All of the stuff that we're interested in for fuels are in this upper right-hand corner. They're the things that are unstable, the things that can be split to liberate energy. Now note that iron 56 is specially called out on this graph, right down here in the lower left. The reason for that is because iron 56 is probably the most stable stuff in the universe, in that anything that is above and to the right of it can liberate energy when the nucleus is split. Anything that's below and to the left of it can liberate energy when the nuclei are fused in a fusion reactor. Iron 56, it's a special case. It doesn't produce any excess energy either way. It just sits there all by its lonesome, nice and happy forever, which is why white dwarfs contain basically just iron 56. That is the end state of most stars. Okay, so like I said, all of the fun stuff is up here. This is where uranium-238, 235, 233, all of the other stuff that we can use for fuel lie. Okay, now that we're talking about radiation and all of the fun things around it, we need to start going into what the common sorts of things that are radiated are and how we can make the use of them, how we can protect ourselves against them, because we're just squishy humans and we don't like being irradiated too terribly much. So alpha decay, you've probably heard of. It is when a unstable particle ejects an alpha particle, which is basically a helium nucleus. When that happens, the atomic mass of the original thing doing the ejecting drops by 4 because you've just released 2 protons, 2 neutrons, and the atomic number drops by 2. A beta particle is when a nucleus ejects an electron. The atomic mass doesn't change because electrons are pretty light in the grand scheme of things, but the atomic number goes up by 1. And you might be wondering where that extra proton comes from. Well, the thing is, the electron didn't come from the electron shell in the atom. It actually came from the nucleus. So what's really happening is a random neutron in that nucleus decided it would be much happier as a proton and released an electron in order to conserve a charge. Inverse beta decay, the opposite happens. A random proton that's hanging around in the nucleus decides it would be much happier as a neutron and releases a positron in order to conserve charge. There are other kinds of reactions that produce radiation. An isomeric reaction injects a gamma ray. There is the possibility of spontaneous fission, electron capture, neutron, proton emission, a few other things. The things that are most common, though, are alpha, beta, and inverse beta, and then isomeric. All of these produce the normal sorts of radiation that you read about and that we have to shield against. Okay, so here's a little bit about radiation shielding. Alpha particles are pretty easy. They're big, they're heavy, they're slow. They can be stopped by skin or even a sheet of paper. Unless you're breathing in radon, which is an alpha emitter, you're not really going to have any sort of interaction with alpha particles that's at all damaging. Beta particles, they're a little bit more energetic, but they're also just electrons. So thin metal or any sort of conductor works just fine. X-rays and gamma rays, that is where we start seeing lead. In the case of gamma rays, a lot of lead because they're extremely energetic. And neutrons, which are, of course, produced in our reactor just as a natural course of operation, this is where it gets weird because neutron interactions depend on how much kinetic energy they have. Neutron kinetic energy is divided into a few categories. Thermal neutrons are about 1/40th of an eV, and they're called thermal because that is the approximate kinetic energy of a gas at room temperature. Low energy is up to about 10 eV, medium up to about 100, and high energy or fast neutrons are above about 100 eV. Now, all of these classifications are important because different materials capture different neutrons in different ways depending on their kinetic energy. And so when we're designing our reactor, we're going to have to account for those different speeds of neutrons, what we're expecting to get out of the reaction versus the materials that we're putting into the reactor to make sure that we can properly capture, reflect, retain, control neutrons in whatever way that we want. Okay, so a little bit of an aside. Physicists like to have fun with units. In chemistry, you get really long chemical names. In biology, they like to use Latin for some completely unknown reason. But us physicists get to have a little bit of fun with our terms. So, some terms that you will see in nuclear physics. There's the barn, which is a measurement of cross-sectional area. It is equal to 10 to the minus 28 square meters. And yes, it does indeed come from the phrase broadside of a barn. An outhouse, well, since they already had a barn, they might as well make something smaller than a barn. They chose the term outhouse. There you go. A shake is 10 to the minus 8 seconds, and it comes from shakes of a lamb's tail. You have a few others that are in use. One of my favorites is the BED, or banana equivalent dose, the amount of radiation that you absorb from eating one banana due to the presence of radioactive potassium in said banana. A very handy unit of measure that you will see all the time in nuclear literature. And, oh, I didn't add it to the slide, but I just learned a good one. Apparently, cosmologists have started to measure dark matter energy density in terms of squirrels per Earth volume. And I'm not sure why. I'll find that out and maybe add it to the slide next time, but squirrels is a great unit of measurement. And I'm definitely going to start using that. Okay. Oh, there we go. So the chemical properties of nuclear isotopes are absolutely irrelevant. If you have carbon in your nuclear reactor and are trying to do calculations, it doesn't matter if that carbon is in the form of graphite, graphene, charcoal, or diamond. To a neutron, it is just a carbon nucleus. So we have some things that are handy for absorbing neutrons. Hydrogen, boron, they really like to eat neutrons. Xenon does as well. These are good for controlling the speed at which your reaction happens. We have things that like to reflect neutrons, carbon, beryllium, lead and tungsten. They also like to absorb neutrons, but in smaller amounts, they can reflect it as well. Now, note that nuclear reflection is not specular reflection like from a mirror. It's more like painting a wall white. So don't think of mirror when you think nuclear reflector. Think more like white wall. Okay. I seem to have lost my mouse. There we are. All right. Now we need some fuels. So fissile, sometimes called fissionable materials, are the things that can undergo fission when hit with a neutron. Obviously, uranium and plutonium are the common examples. Uranium-235 is preferred because the cross section of uranium-235 to a thermal neutron is around 600 barns. Note that we're going to be using barns not as a unit of area per se, but more of a unit of probability. If something is at like a micro barn or one outhouse in probability, it's really not going to happen. Right between 1 and 10 barns is where it's about 50-50, whether the reaction happens or not. 600 barn possibility, it's absolutely going to happen. If a thermal neutron gets anywhere near that uranium-235 nucleus, it is absolutely going to split. So we also have fertile materials. These are materials that can be converted into something else that is fissile. For instance, you've probably heard of thorium reactors. Thorium itself doesn't split, but when it absorbs a neutron with a pretty good probability, it turns into uranium-233, which can be split. And that is where we get thorium reactors. So desirable materials for fuel are, we want it to have a long half-life when it comes to natural decay modes, meaning it's relatively stable and easy to handle. Uranium has a 4 billion year half-life. That's perfect for us. We want it to have a high neutron capture cross-section, meaning the reaction is pretty likely to occur. We need it to release 2 or more neutrons per fission event, just to keep the reactor going. And we would also ideally like it to be relatively abundant in nature. Uranium, fairly abundant. Thorium is awfully abundant. There's a lot of thorium out there. So, you know, those are pretty good fuels for us. All right. Now, there are some isotopes that decay by spontaneous neutron emission or by spontaneous fission. These can be useful in kickstarting a reactor. So, if you go all the way back to that slide near the beginning that shows the big picture of the nucleus with a neutron coming in, well, where does that first neutron come from? It comes from this. It comes from our nuclear spark plug, which is generally a pellet of americium and beryllium that interact with each other to produce free neutrons. You insert this little pellet into a nuclear reactor, and that provides the spark to kick it off. Other materials that are useful, we also have moderators. These are materials that don't completely absorb neutrons, but serve to slow them down. Like I said, uranium 235 works best with thermal neutrons, with slow neutrons. Oftentimes, neutrons that come off of the fission event are traveling very quickly. They're very fast, a lot of kinetic energy. So we need to slow those down so that other uranium nuclei can absorb them. Pretty much any material that works as an absorber will also serve as a moderator. This is why nuclear reactors are generally flooded with water. Water has a lot of hydrogen. Hydrogen is a very good nuclear absorber slash moderator and doubles as a handy coolant for us. Okay, let's put it all together. We're going to start off very easy with the non-reactor reactor. This is the radioisotope thermal generator. Instead of forcing a fission reaction to take place, all we're doing here is getting a bunch of nuclear material, letting it heat up, and then tapping off that heat, converting it straight into electricity. This is useful for a number of reasons, primarily being that it is dead simple. There are no fission reactions taking place, no excess neutrons in the system, nothing that can possibly explode on us. It's great for what it does, which is serve as a very long-lived battery. Here are some real-world examples. Mars Curiosity rover, New Horizons mission. They used plutonium-238, half-life of 87 years. They used about 40, 50 kilograms of it, and were able to produce a couple thousand watts of thermal power, a few hundred watts of electrical power, and they sit there and do that pretty much forever. The largest one created was the Russian research reactor, BES-5. It used uranium-235 and had about 1,000 kilograms of it, not in a reactor configuration, but in a thermal generation configuration. And they were able to get about 100 kilowatts of thermal power and 3,000 watts of electrical power out of it. So, like I said, the advantages of this are it's dead simple. You don't even need any moving parts. There's nothing to control. You can use pretty much any unstable isotope that you have handy, and the operation is absolutely predictable. But it's always on. You can't control it. It's just sitting there producing waste heat and electricity pretty much forever. So it's not terribly useful for propulsion, which is not to say that people haven't tried. Oop, got ahead of myself. There we go. Here is the Poodle thruster. This was built in the 70s as a test article, basically. And it's essentially a resistojet that doesn't require electricity, which is good, but that you can't turn off because it's just sitting there producing heat. ISP is pretty good, about 600 seconds, because you're not actually burning anything. You're just using the residual heat from the isotope to heat up the propellant directly. Thrust is almost none, because this is basically a nuclear-powered hairdryer. Okay, so let's actually make a real reactor that we can control. And we'll use as our model terrestrial power reactors. So this is pretty much how every terrestrial power reactor is made, how pretty much all of them look. You start with a bundle of soda straws made out of something like zirconium, which is basically glass to neutrons. Neutrons don't even see zirconium, it's like it's not even there. You fill some of them up with your fuel. You add control rods, things that absorb neutrons to other straws. You leave a few of them empty. You put the works into a really big coffee percolator, fill it up with water, add some shielding, and stand back. Oop, there we go. So terrestrial reactors are characterized by the fuel that are used, the moderator, what you're using to slow down neutrons if you need to, water, heavy water, salt, whatever. The coolant, which is usually the same as the moderator, though not necessarily so, and the configuration or shape that the core is in. Again, here's kind of what every nuclear reactor looks like. This is a research reactor at University of Texas in Austin. And you can see the bundle of soda straws there in the bottom. This is all in a big pool of water. These things that are coming up through the water are the control rods that can be raised or lowered. You have your fuel in some of the soda straws. Some of them are empty. Some of them probably have instruments in them to measure temperature and neutron flux and things like that. Like I said, pretty much every nuclear reactor that's in use on Earth looks kind of like this. So the first type that we have is the boiling water reactor. This is most like our coffee percolator. Um, the core, soda straws in the middle, heat up the water that's passing through, flash it to steam, steam drives a turbine, turbine spins a generator, there you are. Okay, pressurized water reactor separates out the cooling loop that's inside the reactor from the steam generation loop outside the reactor. And that's just an extra safety layer. So these two types are the most common in use all over the world. There are some 120 nuclear reactors all over the world, and almost all of them are one of these two. Okay, we also have the CANDU reactor, which stands for Canadian depleted uranium. This changes the core geometry a little bit such that you can just use natural uranium. You don't have to separate out the uranium-235 to enrich it. Um, Natural uranium ore, which is about 0.5% of uranium-235, works just fine. Oh, as an aside, yes, you can actually purchase natural uranium ore on Amazon. You can also purchase graphite rods on Amazon. You can purchase heavy water on Amazon. Please don't put them all in your cart all at once. You will probably be visited by the FBI. Okay, there's my disclaimer. All right, people have tried using gas for cooling. None are currently in use for power generation, but there are a few test reactors out there. Um, Same idea with the water cooled, except you're using argon, CO2, helium, some other sort of gas like that for the cooling and moderation. Um, you can see that you can kind of get the idea that maybe we can use this as a means of propulsion. Because, I mean, we're already heating a gas. Why don't we just jet the hot gas out the back? Which is exactly what nuclear rockets do. All right, other types, which I'll go through very quickly just to save a little time. Liquid metal reactors have been tried. Liquid metal reactors are kind of nice because they are often called fast reactors, and they use as part of their fuel cycle uranium-233 instead of 235, or in addition to 235, um, which is very good at absorbing fast neutrons, and so they can burn up their fuel more completely. Um, We also have pebble bed reactors that replaces the rod scheme with a little kind of a gumball machine almost. Yeah, I guess it's kind of a gumball machine where you have pebbles containing fuel instead of rods. Um, Aqueous core reactor was tried once here in the United States at uh, Oak Ridge National Labs in Tennessee. And this was done by dissolving uranium salts in water and then adding impurities to that water to control and moderate the reaction. Some interesting possibilities for propulsion there as well. Traeger reactor is one that operates in pulsed mode. Um, Instead of keeping the fuel rods static, what it does is it fires fuel rods at high speeds through the middle of the core. Reactivity can go very high, very briefly, up to weapons level, but for less than a millisecond. And this is normally used for neutron generation for research purposes, but it also offers some interesting possibilities for propulsion. Okay, so how do we convert all of this work that's been done on terrestrial power reactors into a propulsion system? That's actually pretty easy. We start by getting rid of all of the coolant. We don't need it. We get rid of as much shielding as possible. Hey, there's already radiation out in space. A little less shielding isn't going to be a terrible thing. We add a big tank of cryogenic hydrogen. We run the hydrogen through the core, and we jet it out the back. Piece of cake. And in fact, this was done from about 1958, 1959 through the early 70s in the Kiwi, Rover, and NERVA programs. These were programs sponsored by the Department of Defense. They took place out in, well, Nevada, outside of Las Vegas, and they built a lot of reactors. Note that this table isn't even an exhaustive list. This was just some of the more interesting ones. So these reactors, these engines, were every propulsion engineer's dream because they had ISPs 2 to 3 times better than the best chemical rockets that they had at the time, without sacrificing the thrust. They still had kilonewtons of thrust coming off of them. They had an incredible amount of output power, and the test times were amazing. Some of these, like the NF1 engine, for instance, was fired for 2 hours with many starts and restops. These were beautiful machines, and they all looked something like this. So the thing to note about this rocket engine is how similar it looks to just a regular chemical rocket engine. You still have your turbo pumps, you still have your nozzle, all of that kind of stuff, but the combustion chamber is replaced by this reactor core. This is where your uranium sits, and instead of jetting hydrogen and oxygen through, burning it in a chemical reaction and then jetting it out the nozzle, you just shove hydrogen through, it heats up in the core and goes right out the nozzle. Like I said, pretty much the same as any liquid rocket engine in use today, but with the addition of the core. Okay, there have been, since the NERVA days, a few follow-on experiments and a lot of simulation. The first is in taking that basic NERVA engine and making it bimodal. Since we already have a nuclear reactor, we might as well get some electricity out of it too, because we need electricity also. So let's add a secondary cooling loop and cycle it back, run a turbine. Ta-da, we get electricity too. Yay. Okay. Trimodal, or LANTR, LOX Augmented Nuclear Thermal Rocket, is basically just your regular plain old nuclear rocket, except it kind of has an afterburner. So the idea behind this is, hey, we have hot hydrogen coming out the back. Let's throw in some oxygen while we're at it. The oxygen will burn in the hot hydrogen. And yeah, we'll lose some ISP, but we'll gain in thrust. This kind of thing would be useful for things like orbital braking maneuvers or, anything where you are worried more about the total thrust than the absolute efficiency of the engine. It's basically an afterburner for your nuclear rocket. Okay. I am now going to take another aside and talk about another thing that was researched in the 50s. This definitely counts as a scary concept, but it's also a historical concept. So we're going to look into it for a bit. So this story, perhaps apocryphal, happened around 1956. And as the story goes, a underground test was performed in Nevada on a 100 kiloton or so nuclear bomb. This bomb was placed a few hundred feet below the desert, and The shaft that it was placed down was capped with a manhole cover. When the bomb was detonated, there were high-speed cameras trained on this shaft. The camera recorded the manhole in just a single frame, but from the timing of that, a lower limit on its speed could be figured. And they've decided that that manhole cover was launched away from the Earth, possibly leaving the solar system, going at a good 65 kilometers per second. Now, like I said, the story might be completely fiction. No one really knows. But some nuclear engineer possibly heard that and said, hey, this gives me an idea. So how can we move fast by blowing things up? Again, bear in mind, this was the 50s and 60s. They were a little bit less concerned about safety then. So let's take a small nuclear bomb, maybe a few thousand of them, 10 kilotons or so. We stuff them into an ejector system, kind of like cans of soda in a vending machine. We'll toss them out the back of the spaceship, about 1 per second, and detonate them. We'll use a pusher plate or gasp, maybe even a parachute, and ride that shock wave. This is the Orion concept. Again, made popular in the 50s and 60s, but thankfully never actually built using actual nuclear devices. Anyway, ISP is fantastic. 50,000 seconds, incredibly efficient. Because you're not dealing with thermodynamics of combustion, you're actually riding a detonation wave. Thrust can be meganewtons because, again, you're riding a detonation wave. Vehicle mass is insane, and the environmental impact, well, we don't really talk about that. These were the actual Orion designs that were put on the drawing board, ranked in rough ascending order of crazy. Note that the smallest ship mass, 300 tons, is still almost as large as the International Space Station. This is the smallest one. It had a diameter of 20 meters, using 25-ton bomb yields, 500 of them. And this was considered about what you would need to get to Mars. And they just go up from there. Ship masses of thousands and even millions of tons were considered. At the extreme end of the spectrum, there was an actual design on the drawing board for a 40 million metric ton ship with a diameter of 20 kilometers and 30 million bombs, each of 1 megaton yield. And this was calculated to be the rough size of a craft that you would need to get about 1,000 people to Alpha Centauri in a reasonable time frame. Yeah, somebody actually thought these were good ideas. And note that there might not be enough fissile material on the planet to make that last one, but that's okay. The takeaways from this are not that we're going to ever build such a thing, but if we ever had to get off the Earth in a hurry, like there was some, I don't know, neutron star about to crash into the planet or whatever, Orion would be about the only way that we could do it right now. Orion is also a very useful model for any high energy pulsed propulsion system. Maybe if we turned the fission bombs into fusion pellets, we might be onto something, which is an entirely different lecture, and so I'll leave it there. Okay, let's get back to what we can do in a safe-ish and controlled-ish way. So our basic problem is that nuclear thermal rockets are heat engines and subject to the laws of thermodynamics. In particular, the hotter they are, the more efficient they are. So, in terms of upping the temperature, we can just let the core melt. Here on Earth, that leads to Chernobyl. But up in space, we can use centrifugal force to keep the fluid core kind of where we want it to. Uranium fuel rods melt somewhere between 1,500 and 2,500, depending on the exact alloy, and vaporize at around 4,000 Kelvin. So, again, we'll just let the core melt. Liquid core will give us an ISP of about 1,500 seconds, so about twice what a solid core can. But if we keep upping the temperature, droplet core is at around 7,500 Kelvin and injected as a wet vapor. and ISP is bumped up to 2,000 seconds. Note you start to get into engineering difficulties because now your core wants to escape out the nozzle. Um, but, since we've come this far, why don't we just let the core flash all the way to a gas? And this is where we come up with the gas core or nuclear light bulb. Enriched uranium hexafluoride gas is contained in quartz bulbs. We pass hydrogen around the bulb fast enough to keep the quartz from melting. Because the core is so extremely hot, ISP can go up to about 5,000 seconds. So a good 5 times what the best solid core rocket can do, and a good 10 times what the best traditionally fueled liquid propulsion system can do. And with that, thrust can still be in the meganewton range. Now, of course, there are engineering difficulties. You have to keep that hydrogen flowing around that quartz tube because you don't want your quartz to vaporize also. How do you even throttle such a thing? How do you control the gas flows around it? There's, again, a lot of engineering difficulties, but in the near term, this might be the best that we can do without actually detonating bombs. Like I said, 5,000 seconds of ISP, that's as good as, or better than even our best electric propulsion systems without sacrificing any of the thrust that we get. Okay. I'm going to step back very briefly. And we're going to start to get away from things that are heat engines, because that's the basic problem that we have. All of these things are thermodynamic heat engines and subject to laws of thermodynamics. So let's try other means of extracting energy without traditional heat exchange. So remember the tritium reactors. Every time they pulse, they generate as many prompt neutrons as a nuclear bomb. Well, neutrons are handily absorbed by hydrogen, and so they can kinetically, or they can transfer their energy not through thermal transfer, but through quantum mechanical transfer. Since you're not transferring them thermally, the laws of heat engines don't matter, and you can get a lot more efficiency. In theory, the propellant can reach temperatures far beyond what's in the reactor core because you're coupling quantum mechanically instead of thermodynamically. And so you can get insane efficiencies up to around 100,000 seconds. Now, the downside of these schemes is that the thrust drops. Again, we have that problem of very high ISP. A fission fragment reactor, for instance, can have an ISP of 1.5 million seconds, but the thrust is best measured in hummingbirds. A hummingbird being about 50 millinewtons of thrust. I guess this is probably a standard hummingbird. I don't know if there are differences in terms of species, but hummingbird. Anyway, again, what we want is something that is both very efficient and very, very high thrust. Okay, which brings me, like I said, I'm going in order of scariness here. It brings me to the last one. This is the scary. This is the granddaddy of scary. This one is from Robert Zubrin and is dedicated to all of those people who really like the idea of Orion, but don't think it's quite explodey enough. Can we do better? Sure we can. This is the nuclear saltwater rocket. So what we're going to do is we're going to dissolve highly enriched uranium salts in water. We're going to contain these in hollow rods made of some sort of neutron absorber, borated steel, something like that. We're going to use a series of pistons to evacuate all of these rods into a chamber all at once. When the streams cross, when all of this liquid uranium hits all of the other jets of liquid uranium, they go prompt supercritical pretty much instantly. And here's the important part. They will continue to do so until you are out of fuel. So essentially, this is a megaton-class nuclear weapon that just never stops exploding. Normal nuclear weapons, bang, they go off, they're done. This one, no. No, it just doesn't stop. It just keeps going. Here are the stats on the nuclear saltwater rocket. Thrust from Zubrin's design, 15 million newtons. So as good as the best chemical rockets that we have now. ISP, 500,000 seconds. Because once again, you're effectively detonating a weapon. Chamber temperature and pressure were too high for him to even accurately calculate. But if you want an Epstein drive like they have in the Expanse, this is it. This can get you anywhere in the solar system, anytime you like, no questions asked. All right. On that note, I am ready for questions.
Well, thanks so much, Jim. I mean, that's really a lot of exciting info all in a compact presentation there. I mean,
Oh,
yeah.
I can and have gone on for many, many hours. And if you come to the AIAA SciTech in Florida in just a few weeks, I will be there sharing some sessions, moderating a few others. You will hear many hours of exactly this kind of thing.
Oh, that sounds like fun. Yeah. Yeah. Well, maybe some of our participants would like to go. And speaking of our participants, some are starting to put questions into the chat. So if you want to take a look at that, or I could just read out the questions.
Yeah, no, I taking a look at this now. Okay, will protons ever experience radiation shielding? Okay, so protons are a bit of a special case. They're heavy like neutrons, and they are fast, slow. The way that they're absorbed is kind of like how neutrons work. But they are also charged, which means any sufficient amount of metal is generally good enough shielding for them, just because they will start interacting with the electron clouds in the atoms of those metals. So they are pretty easy to shield against and don't generally fall into any of the calculations.
All
Okay.
right.
Um, let's see. Question about the slide radiation shielding. Wouldn't the kinetic energy of an alpha particle change its total energy as well, since there are neutrons in there? Yeah, but neutrons that come out of a nucleus as a result of fission come out singly, which means that their kinetic energy isn't divided by four like in an alpha particle where they're still bundled. And part of the energy of an alpha particle is contained in that bundling as well. So alpha particles are pretty much extra slow. Um, and because they are two protons and two neutrons and happy as a unit, they don't really interact with a whole lot in the same way that neutrons do. They're not generally captured by anything. They'll pick up a few electrons and just become helium. And as a side note, um, helium on Earth is mined. It comes from underground, oftentimes found with natural gas pockets and that kind of thing. And most of that helium comes from alpha particles, from radioactive decay of elements underground and alpha particles capturing electrons and turning into helium. That is where most of the helium on our planet comes from.
And if I can ask real quick, because I've wondered how well distributed around the world is that helium? Because we've heard about the National Helium Reserve and such. Is it
It's
important to keep those few natural gas wells that have helium in it available, or is there just a whole lot of it? We just haven't tapped it all around the world.
We don't know because there's not really a whole lot of incentive yet for people to start looking for helium mines as helium mines.
Mm.
Right now, there is enough to satisfy demand just as sort of a side project of natural gas mining.
Mhm.
If we start researching helium mines for helium mines, we might find a lot more, but there just hasn't been the economic incentive yet.
Okay, because some people have wondered, are they wasting a valuable resource by buying a helium-filled balloon? Because of course we know it's just not going to leak out. So it's going to get wasted. Okay, thanks. That's an aside. But yeah, so we've got some more, not only in the chat, but I think a couple of folks online would also like to ask live questions. So I'd kind of like to go back and forth. So before we get to the warp engine, how about if we go to someone online who'd like to ask a question
Sure.
verbally?
I have a question.
It's Mike.
Um, the answer to this is probably buried in your presentation, which is excellent. And I have to go back and look at it some more. But it used to be that fission reactors were not good because on Earth to produce energy because they provided a lot of radiation waste particles. And and the hard part is what do you do with this radiation waste? And if you put it in barrels and bury it underground, the radiation lasts longer than the barrels, and so soon the radiation will get into the water supply and maybe even pollute the ocean. So how do you clean up the ocean with radiation waste and so forth? So the question is, have they been able to use fission reactors and control the radiation waste, or do something with the radiation waste to recycle it in some way, or to do something with the radiation waste so that it won't get into our air or water supply?
The short answer is yes, and this is really more of a political will as opposed to physics kind of issue. So here in the United States, we have a much bigger problem with radioactive waste because we don't reprocess. And this is due to nuclear material proliferation concerns. As part of reprocessing fuel, you separate out other things, the krypton, the, strontium, the plutonium. And you know, then recycle all of it into new fuel rods, which great idea. You can reuse fuel rods pretty much indefinitely that way. But you also end up with plutonium, which theoretically somebody could steal and make nuclear weapons out of, which is why in the United States we have a once through and done policy, unlike everywhere else in the rest of the world who reprocesses nuclear waste. For instance, France, they have as many reactors as we do, and they have no problems with radioactive waste. Neither does Switzerland, because they do this reprocessing. They burn up their fuel almost completely. Now, it should also be noted that we're not talking about a lot of radioactive waste here relative to other energy systems. For instance, the Palo Verde reactor in Arizona is one of the largest in the world, and the amount of radioactive waste that they generate every year could fill up the back of a pickup truck with a little bit of room to spare. So, that's about how much we're talking about. Um, yeah, it is a concern, but again, it's more of a political will kind of thing than a engineering kind of thing. If the United States were to do reprocessing of radioactive waste, we would have isotopes for medical purposes, for research purposes, to power space probes using RTGs, and we wouldn't have a waste problem anymore. But there's that political thing where we don't want to produce things that other actors could theoretically get their hands on if they stole a bunch of stuff from a processing facility. So there
Okay,
we are.
and and uh, and so the other side of the question is with fission reactors. I believe they do not produce as much radioactive waste at all as fission reactors. And so, how close are we to using fusion reactors for energy production on the Earth?
We're actually pretty close. The thing about fusion reactors is that they are not self-starting or self-sustaining. A fission reactor, you just put everything together, stand back, and it does its own thing. Fusion has to be forced, contained, and given energy through magnetic fields, through lasers, through RF excitation, through all these different means to add energy to the system in order to keep the reaction going. And that's always been the hard part. But due shockingly enough to advances in AI and neural control systems, we are really close, like a good 10 years away. In fact, we've already gotten net power out of a number of fusion reactors here on the ground. Um, and right now, it's just figuring out how to best commercialize it. But new control systems and research into AI and neural networks for control are what kind of cracked that open in the last 10 years or so. So, go figure. So yeah, we're pretty close. And for propulsion, fusion makes even better systems than fission does. It's more efficient. It uses hydrogen directly. And it's a fantastic idea. And of course, fusion itself is a whole nother presentation that I could spend another hour on easily. So,
Good, good. How about we go back to the chats again, Jim?
sure. Okay. Were the Star Trek warp systems like Orion? No, they were warp drive. So again, that is another presentation entirely. But yeah, we are actually doing research now into is called the Alcubierre warp metric and its various derivations of modifying the fabric of space-time to push a spacecraft forward, basically riding a ripple in space-time, almost like a surfer rides a wave. Um, Doing that, you come pretty close to having a warp drive, kind of like how it was envisioned in Star Trek.
Mhm.
So no, not nuclear at all, something entirely different. So there we are. Okay, current state of nuclear propulsion. This is getting more active all the time. And in fact, there are a number of test engines currently under construction and test reactors being built. Ones that you might hear about them. Um, this is always an interesting question as to how much I'm allowed to say about them, and so I'm just going to shut up. But but yeah, there are currently systems being built.
Okay.
If you look into any kind of nuclear research, you start to hit walls about like, oh, can I mention this? Can I not? Best play it safe.
Mhm.
Um, okay, is the word Barnes a unit of measurement specifically for isotopes? No, it's actually just a general unit of measurement used by any sort of particle physicist. They use that unit of measurement at CERN all the time, and it's pretty much always used as a measurement of probability. Um, it's used in slightly different ways depending on the reaction. But yeah, CERN particle accelerator folks use Barnes all the time as well.
I can
Oh,
just imagine a sentence in French with the word Barnes embedded right in the middle of it. Yeah.
yeah.
Okay, keep
Oh,
going.
there's also nuclear waste vitrification that you cannot spill because waste is in the form of glass. That is absolutely true. Um, Yeah, it's the theory behind vitrification is, well, it came out from the ground as a form of ore. Why don't we just make it into ore and put it back in? Yay, good for us. So yeah, that works very well as well. And good use of the Alcubierre. Yes, the Alcubierre warp metric requires negative energy. And actually, we do know that it does exist because we can create it on very small scale using the Casimir effect, which was first experimentally confirmed just a few years ago. We can create regions of negative energy. We can create little teeny areas where the vacuum is just a little bit more vacuumy than the vacuum around it. So
Okay.
yeah, I mean, there might be a path there to making use of warp fields in the future.
Wow. So yeah, that really sounds advanced. Okay. All right. So any more verbal questions from folks? You can just unmute and ask. So yeah, the thought of the negative energy just reminds me of how in semiconductors you can have electrons moving and you can have holes moving. So the lack of
Yes.
electron, and so yeah, the idea of negative energy. That's the first thing I thought of is that it's the lack of something that's moving on the other side of zero.
Hmm.
Yeah.
Yeah, kind of
One question.
Yes,
sure.
John.
Um, has Jim thought of maybe being a graduate instructor at one of the Texas universities?
I've thought about it as a retirement job. My wife and I have talked about like moving back to the Southwest and I've been offered a couple of things at the University of Huntsville, at Emory-Riddle. It's like, once I get tired of the consulting thing, yeah.
Lots of options. I'm sure you have.
Lots of options.
Yeah, great demand for your skills and knowledge. Yeah. Okay. Thanks, John. Any other verbal questions?
Well, I
Any-
have one.
Yeah.
So you had another term called outhouse.
Yes.
And so I was wondering just how often are outhouses used?
About twice a day, depending on the person.
That's what I was guessing.
I mean,
Uh,
I'm a little older, so for me, it's like 3 or 4 times a day.
yeah, I can imagine people are expanding and contracting from the barn, the broadside of a barn
Yep.
scale
Yep.
for really small scales. Yeah. Okay. Anyone else want to type into the chat or ask verbally? I mean, this has just been so enlightening, Jim. Really appreciate.
Glad you enjoyed it. Like I
Yeah,
said, I'll be emailing you these slides. It's just a PDF. So,
good. Thank you. Yeah, we'll make those available. And so, yeah, AIAA always does a great job of disseminating information to folks. And of course, if you're ever in the Houston area on a third Thursday of the month, we have our local social, and we'd love to see you and your wife out here for that if you happen to be passing through or whatever.
yeah.
And yeah, because everybody, of course, ends up talking shop and exchanging lots of ideas and things like that
Oh,
at those
absolutely. And
socials.
I love the Houston area. I've always had fun every time I've been over there.
Okay. And I see Esther's put another question into the chat.
Oh, okay. Is there a way to go about excuse me, determining if a nuclear isotope will have a half-life? Well, everything that decays has a half-life. That's, just, but if determining if it decays or how it decays, yeah, you put it into a particle detector and watch. Um, you know, Measure the amount of stuff and what kind of stuff comes off of it. And that's really the only way. I mean, there are issues with doing that with very long-lived isotopes. In fact, I forget what species it was, but they just discovered that a particular isotope of a particular element has a half-life. It's actually not stable like everyone thought, but actually has a half-life of something like 100 quadrillion years or something like that. And the way that they figured that out was by having a big sample of it and sticking it into a detector and waiting and then getting lucky and catching a single decay event and being able to extrapolate from that. So
Well, kind of what I've always had in my mind, you talked about stable. In my mind, everything could decay because we just
that's
don't know what
true.
particular nucleus is going to want to do. It's just that the time scales get to be so long. The one you mentioned, of course, is way longer than the age of the universe.
Mm-hmm.
And so it just comes down to what that one particular nucleus decides it wants to do in a time scale much greater than the age of the universe. And so, yeah, stable is
Absolutely.
just kind of relative to how long you want to wait.
Yep.
So, yeah, there's things that we just can't determine because the time scales are not only longer than a human lifetime, but any imaginable amount of time.
Exactly.
Yeah, yeah. So good. Okay.
Can I ask a quick question?
Yes,
Sure.
please.
So how might a young engineer go about getting involved in this area of research and development?
Okay. There are a number of schools right now. This is primarily the domain of government research laboratories and academia. There are a number of schools that are very active in this. University of Princeton, if you're a fan of fusion. Um, University of Michigan, University of Huntsville of Alabama at Huntsville. Um, Caltech has an interesting program. They're doing some interesting work on fusion as well. Yeah, there are a few academic institutions that are really into this kind of thing. And then there are, of course, government labs that are very much into this kind of thing. You have all of your classic ones. Los Alamos is of course the most famous. Oak Ridge National Lab, has is doing research on this kind of thing. But then there are also some of the lesser known ones. Idaho National Laboratory. Um, let's see. Oh shoot, what's the one in Santa Fe? Sandia. Sandia has a fascinating program for nuclear propulsion research. So, yeah, it's primarily academia and government laboratories right now. That said, pretty much every aerospace company has its own little research program going on. Um, I know that Blue Origin does. I know that uh, SpaceX does. I know that um, Boeing does as well. So there's little nuclear departments in most aerospace companies right now, and that'll probably get bigger.
Very good. So thinking you mentioned SpaceX, and of course the propulsion isn't nuclear, but what do you think of the propulsion for the SpaceX Starship and the Super Heavy using the liquid methane, and then of course you have boil off up in space. What's your opinion on the choice of that chemical?
Well, in general, I mean, I, it's a beautiful machine. It really is. And,
Yes.
I very much appreciate the work that they've done on the Raptor engines, that Blue Origin has done on the BE3 and BE4 engines. Ultimately, from a civilization spanning time point, traditional chemical thrust is a dead end. It's
Mhm.
too inefficient, too heavy. It just makes no sense if we're going to actually be a multiplanetary species. If, these tech billionaires really wanted to do something to move a lot of stuff off of the Earth, then they would just bite the bullet and build an electromagnetic rail launcher off the coast of South America, because that's, the best way to get stuff into orbit, in terms of efficiency. Of course, it would cost $100 billion to build a prototype that may or may not work, but, which is probably why they didn't. But, um, so yeah, I appreciate a good quality machine, in much the same way that I appreciate a good Swiss watch, even though I'll never need one, or a good, um, classic muscle car engine, even though it would be silly to, buy and maintain one that gets like 5 miles to the gallon. It's a great piece of machinery, but ultimately an evolutionary dead end on our path to the stars.
So quick question, since you mentioned electromagnetic railguns. Of course, in literature, they've talked about having them on the moon to get materials that we may want to mine on the moon in the future off the surface of the moon and into orbit. But I didn't think it was practical on Earth because of our dense atmosphere. I thought it was just not a very good way to do things. You mentioned, of course, and I'd heard about it before, the manhole cover that got launched into space.
Yes.
But who knows what condition it was in after it passed through a lot of the Earth's atmosphere.
Right.
And obviously, we want to keep something pretty much intact if you want to use it, launching it off the Earth with an electromagnetic railgun. But would it work through the Earth's atmosphere?
Well, it would if you start slow and go up the side of a handy mountain such that so the Earth's atmosphere, as a rule of thumb, every 14 to 15,000 feet, the air pressure drops by half.
Yeah.
So, 14, 50,000 feet, you're at half air pressure. 28 to 30, it drops to about a quarter, another 14, 15,000 square feet after that, it drops to an eighth, etc. So, there's a handy mountain right off the coast of Ecuador, that goes up to about 21,000 feet. Um, and it's just a couple of degrees off the equator.
Mhm.
And, if we threw a few hundred billion at Ecuador, they would probably be happy to loan us the land leading up to the top of that mountain.
Mhm.
And, we could build a railgun to get us out of, up to Mach 3, 4, 5, something like that. And certainly, terrestrial rocket sleds have gotten that fast. There are rocket sleds that were used by the military for testing that got to Mach 6. So, there's some precedent here. And if you make a nice, long, gentle rail gun up the side of a mountain that can get you up to Mach 5 or 6, um, it'll get you out of the worst part of the energy condition for getting into low Earth orbit. You can save a good 3/4 of your fuel and build an actual single stage to orbit vehicle that way.
Mhm. Okay. Very good. Yeah, that I hadn't thought about the details of it as precisely as that, but that verifies that it could be done
It
in a
can be done.
practical sense. You're not just throwing a blob of iron up that's going to half melt or something. Yeah.
Right, right. I mean, the idea is that you want to keep it to like 3G-ish for us squishy humans. I mean,
Mhm.
someone in the comments just mentioned spin launch. And yeah, that's great for propellant or for, ruggedized electronics.
Mhm.
But, you're never putting a human or anything living through spin launch, that's for sure.
Ah. Okay. And actually, when I was asking, I wasn't even thinking about for humans, just thinking about materials that we want to get into space. But yeah, like you say, if you can actually design it to stick to say below 3Gs, I guess then would work for humans. Yeah. Okay.
Yeah, I mean, keep it to roller coaster levels and you'll be fine, right?
Yeah, yeah, it's the ultimate roller coaster that kind of like
Yeah.
some of the movies that go flying off the end. Yeah.
Hmm.
Yeah, yeah. So, okay, good. Yeah, thanks, Daniel, for the extra comments there in the chat. So more questions, either verbally or typed in. I mean, as you said, Jim, this could go on and on and on
Oh,
because
yeah.
there's just so much territory to cover. And yeah, so um, what about other countries around the world, China or others looking into nuclear propulsion in space? Are there a lot of things going on?
Well, the ESA has a tiny research program.
Hmm.
They're the only ones that we know about. Theoretically, Russia and China have programs as well, though they aren't talking about them, and our military probably knows more, but they're not telling us.
Hmm.
So, yeah, there we are.
Yeah. Okay. Well, obviously, any big demonstration out in the open would be visible to the whole world, and we
Oh,
haven't seen
yeah,
those. Haven't seen
absolutely.
those, so we know they're not to a demonstration stage.
Hmm.
Yeah. Okay. Yeah. Yeah. Everything around the world gets observed by satellites in space or from balloons floating over international borders. Yeah.
Yep, yep.
Good. Good. So. All right, folks. We'll wrap it up then if there are no
All
further
right.
questions. And this has been
Thank
really
you very
fun.
much.
And yeah, we've gotten to learn a lot today. And so, folks, you'll be able to get a hold of the PDF of the slides later on. And so we will end the recording at this point. So, but just to start with, I'd like to say thank you very much, Jim. That was really exciting. And yeah, Zoom talks are always still a little bit different than in-person talks, but we
Sure.
thank you greatly. And so let's see here on the recording side, we'll
Yeah,
stop.
thank you very much. I had a lot of fun.